Hi, so I'm Susanna di Rezende, and this is joint work with Jakob, Tony, and Robere. So I'll be talking about KRW composition theorems via lifting. Okay, so in complexity theory, we're interested in understanding how hard it is to compute functions. So here, the model is going to be Boolean circuits. These are circuits with OR and NOT gates. And for the purpose of this talk, we'll only be focusing on circuits with fan-in 2. Okay, so the measure that we'll be interested in for this talk is going to be the depth. So d of f is the minimum depth required to compute the function. So it's the depth of the shallowest circuit that computes f. It's not hard to see that if we have a function f that depends on all n variables, it requires depth at least log n. And this is because we're only considering circuits of fan-in 2. Okay, so what are these functions that can actually be computed in very small depth, in depth O of log n? Right? So this class of functions is denoted by NC1. And an open problem in complexity theory is, does this class contain all functions that can be computed in polynomial time? Is P equal to NC1? Or can we show some explicit function that requires depth at least little omega of log n? And actually, it's surprisingly difficult to prove depth lower bounds. The best lower bound we can prove so far is simply 3 times log n. And this has been known for over 20 years. Hostad proved this in 98, and since then, the only improvement has been in this little o factor. So in order to address this P versus NC1 question, Karchmer-Wigderson, they proposed an approach. So what they showed is that it's enough to understand composition of functions. So, okay, let's define what composition is. We have two functions, f and m. We have two functions, f and g. Here the composition of f and g is denoted by this diamond. And the input of the composition is an m by n matrix, where m is the arity of f, n is the arity of g. And it's the following function. So on the rows of x, we apply g, and thus obtain this vector A of dimension m, on which we apply f. So this is the function f composed with g. If we would like to build a circuit that computes this function, a natural way of doing this is first considering a circuit that computes f, and then instead of the variable inputs of f, we add circuits that compute g with the corresponding rows of the matrix X. So this is a circuit that computes f composed with g, and it clearly has depth d of f plus d of g. So we know that the depth required to compute f composed with g is at most the depth of f plus the depth of g. And what became known as the KRW conjecture states that this is essentially optimal. What KRW showed is that if we could prove the KRW conjecture, then we would be showing that P is not equal to NC1. So in this sense, it's enough to understand composition of functions. Okay, so what we know so far regarding the KRW conjecture is that it holds for any f, but only when composed with two specific inner function g's. Now, before going into what the general approach has been to study the KRW conjecture, I'd like to first state our results. This is going to be very informal. So our motivation was that the KRW conjecture is only known to hold for these two specific g's. So if you want to make progress towards proving the KRW conjecture, we would like to extend this for more g's. And here we have we hit a certain barrier, which is that the way it has been shown to hold for these two specific G's requires a very good understanding of the depth complexity of G. And we don't have so many functions for which we do understand the depth complexity well. But there are many functions for which we understand the monotone depth complexity well. So for this reason, we consider the monotone KRW conjecture. So the monotone KRW conjecture can be considered as a step towards proving the full KRW conjecture, but it's also interesting in its own right, and it's still open. We make progress towards proving the monotone KRW conjecture, so we show that it holds for any f and for any g such that g's lower bound can be obtained via lifting. Okay, so for this talk, it won't be very important exactly what lifting is, so we can simply think of it as a method for proving lower bounds. I'd like to point out that these g's for which our theorem holds includes classical functions such as ST connectivity, click, or the gen function. So this is great. We can actually extend the range of inner functions that we can handle. But this is in the monotone setting, and our ultimate goal is to prove the non-monotone KRW conjecture. So in order to get closer to this non-monotone setting, we define the semi-monotone KRW conjecture. And we see this as an important contribution of this paper because it's a way to get from the monotone version to the non-monotone version. So in this setting, we show that this semi-monotone KRW conjecture holds for the universal relation when composed with any inner function such that we can prove the lower bound of this inner function via lifting. Okay, I won't get into exactly what this universal relation is, but let's just think of it for now as a simplification of a function. The way the KRW conjecture has been studied is via communication. So in order to explain this, I have to define the Karchmer-Wigderson game. So this is a communication game between two players, Alice and Bob. There's some function that they both know. Alice receives an input in the preimage of 1. Bob receives an input in the preimage of 0. So their inputs are clearly different. And their goal is to communicate to find an index where their inputs differ. And they communicate according to some pre-established protocol, which can be viewed as a tree. So at every node, there's one player that speaks, that sends a bit, and at the leaves, they should output an answer to this problem. They should output an index where their inputs differ. And they want to do this minimizing the amount of communication. So C of KWF denotes the minimum communication required to solve the KW game on F. And if we think of this measure in terms of the protocol tree, this is simply the depth of the tree. Okay, so this is an interesting model, but how does it relate to circuits? So what Karchmer and Wigderson showed is that the depth required to compute a function is equal to the communication required to solve the KW game on F. I don't have time to get into the proof, but I wanted to at least show this slide so that you see that these objects look related. Okay, so with this view, this connection in mind, we can rewrite the KRW conjecture in terms of communication. So what the KRW conjecture says is that the communication required to solve the KW game on the composed function is approximately equal to the communication required for solving the KW game on F plus the communication required for solving the KW game on G. From now on, we're going to view the KRW conjecture from this communication perspective. Okay, so let's first see what this game of the composed function looks like. For convenience, we're going to denote this as KW of F composed with KW of G. And this game is as follows. Remember that the F composed with G maps a matrix to 0, 1. So this means that Alice receives as input a matrix in the preimage of 1. Bob receives as input a matrix in the preimage of 0. and their goal is to find an entry in this matrix where their inputs differ. One way of solving this is that, well, they can apply G to each row of their matrix. Thus, they obtain two vectors. Alice obtains A, Bob obtains B, and they know that if they apply F to these vectors, Alice will get a 1 and Bob will get a 0. So they can simulate the KW game on F in order to find a position on these vectors that is different. Once they find this position, they know that if they look to the corresponding rows, those rows must be different because G applied to this row gives different values. So now they can simulate the KW game on G on this row and find an entry of the matrix where their inputs differ. Okay, so this is showing that the communication required for the composed problem is at most the sum of the communication required for the two separate problems. And again, what the KRW conjecture is saying is that this protocol is essentially optimal. So what do we know regarding the KRW conjecture? So there's been a long line of research, and it basically culminated in these two results. So on the one hand, we know how to show that it holds for every outer function f when composed with the universal relation. So now I can actually say that the universal relation is a simplification of the KW game on some function. So we know how to prove it for in this case, and we also know how to prove it when the inner function is parity. And that's basically it. Those are the two cases that we can show that the KRW conjecture holds. So it seems that, okay, we're still far from proving the KRW conjecture. But there is one piece of good news. It's that we don't actually have to show that it holds for every inner function G. It's enough to prove that it holds for the multiplexer relation. So what Meir showed last year is that if we could show that the communication required for solving the KW game on F composed with the multiplexer relation is approximately equal to the communication required for solving the KW game on F plus the communication required for solving this multiplexer relation, then we would also get P is not equal to NC1. Okay, there's a minor technicality here on how this communication is defined, but this is essentially what the result says. So this is good news. We only need to show it for this one relation. So we already know how to show it for the universal relation, for the KW game on parity, and now we only need to show it for multiplexer. But this seems like a harder problem. We don't know how to show it for multiplexer. An intermediate goal then is to show the KRW conjecture for more complex inner functions. As we mentioned before, here we reach an obstacle, which is that the way these results were shown is that we somehow need to understand the communication required for solving these problems very well. And there are not so many functions for which we understand the KW game on these functions well. So actually we don't have other candidates for which we could extend these results. In the monotone world, we do have several functions for which the monotone version, which we'll see in a minute, of the KW game is well understood. So these include ST connectivity, click, the gen function, matching. So there's this natural question, can we actually show that the monotone KRW conjecture holds? Okay, so let's see what the monotone KRW conjecture is. It says that the monotone depth, that is the depth of the shallowest monotone circuit that computes F composed with G, is approximately equal to the monotone depth of F plus the monotone depth of G. In order to state this in terms of communication, we need to define the KW game, the monotone version of the KW game. So remember that the KW game, we had some function F, Alice received an input in the preimage of 1, Bob received an input in the preimage of 0, and they had to find an index where their inputs differ. In the monotone version, the difference is that there's a monotone function f, and their goal is to find an index where Alice has a 1 and Bob has a 0. So now note that this index exists because this is a monotone function. Okay, and what Karchmer-Wigderson showed is that the monotone depth required to compute a function is equal to the communication required for this monotone KW game on F. So the same connection holds in the monotone world. So again, we can now write the monotone KRW conjecture in terms of communication. Okay, so now we can state our monotone result. So we showed that for any F and for any G such that the lower bound for this monotone KW game on G is proved via this lifting theorem, then the monotone KRW conjecture holds. So as I said before, this includes G's such as ST connectivity, click, and the gen function. It basically includes every monotone function for which we know how to prove a lower bound except for matching. So let me just give an idea of how the proof works. The proof has two steps. In the first step, we combine these two previous results to show that it's enough to prove a lower bound on a simpler problem. So namely, that the problem is that given several instances to the monotone KW game on G, Alice and Bob should solve one of them. And we assume that prior to the communication, the players already know a bit of information about each of these instances. This is the first step. Now, in order to show a lower bound for this simpler problem, we prove a generalization of this lifting theorem, where we are able to handle the case when prior to communication, the players already have some information on the input. Okay, so this is our monotone result. Now, our semi-monotone result, we define semi-monotone composition. So here we have that the KW game on F, we consider the non-monotone version, but for G, we consider the monotone KW game on G. And here's an informal definition of what this composition is. So remember that in the standard composition, one way of solving this was to first find entry in these vectors A and B such that they're different, and then considering the corresponding rows and solve the KW game on G on those rows in order to find a position in the matrix where Alice and Bob have a different input. Well, Alice and Bob could also consider other rows, not only rows where AI is different from BI, but for those rows, there might or might not be a solution. I mean, it might be the case that on those rows, Alice and Bob have exactly the same input. Okay, so the semi-monotone composition, what changes is that instead of considering the non-monotone version, we consider the monotone version of KWG. So on rows where AI is different from BI, Alice and Bob have to solve the monotone KW game. So with this definition of composition, we can define the semi-monotone KRW conjecture. We can also define a simpler version of this conjecture, which is instead of the KW game on F, we actually have the universal relation. And what we prove is that this simpler conjecture is true whenever G is such that we can prove the lower bound of this monotone KW game on G via this other lifting theorem. Again, this includes G's being SD connectivity, click, and gen, but not matching. Okay, so let's briefly see the main ideas behind this proof. So it uses the Rezende rank method, which is a way of proving a communication lower bound by showing that there exists a matrix A that satisfies two properties. So the first property is that the rank of A is large. And the second property is that if we consider the rank of A restricted to certain monochromatic rectangles, then this rank is small. These monochromatic rectangles are when we view G as a matrix. Okay, so this lifting theorem, this gives such matrices for the monotone KW game on G for several Gs. And we use this matrix to construct matrix for this composed problem. And that's how we obtain this result. Okay, so now take-home message. KRW conjecture is a promising approach for proving that P is not equal to NC1. Here we extend the range of inner functions that we can handle to include ST connectivity, click, the gen function in the monotone setting for any outer function f, and in the semi-monotone setting, but only for the universal relation. And here are two open problems. So one is to extend this semi-monotone result to hold for every outer function and not only for this universal relation. And the other obvious open question is to prove the full monotone KRW conjecture. If we don't want to be so ambitious, we can at least try to extend this to include matching as an inner function. Okay, that's it. Thank you.